This is the last video on volume, and it's going to deal with the washer method. So what I want you to consider is the same thing we did with the disk method, except now we're going to have a little gap where our rectangle actually does not touch the axis of revolution. And so we're going to try and revolve this around, but there's always going to be a gap. So instead of that solid disk that we would get from the earlier lesson, now we're going to have a circle or a gap on the middle where we have to think of taking volume away. So an easy way of thinking about that is to find the area of, or I'm sorry, the volume of the just a normal disk, and then take out a smaller disk from that. So if we were to take this rectangle and rotate it around, I want you to think about, first of all, finding just a solid disk. And I'm not going to try to draw this for you because it will not look pretty. But if we were to find the volume of the outer cylinder, and then we're going to subtract the volume of the inner cylinder, this is what it would look like. And I know we wouldn't necessarily have to solve it quite like this, but the outside cylinder, the area of the circle would be pi times 8 squared, because the radius would be 3 times 5. And then if we see the width of that rectangle is 2, we'd have to multiply by a 2 at the end. And then we want to take away the cylinder that's created from that inside gap, and so that cylinder would have a volume of pi times the radius squared, so pi times 3 squared, and still with a width of 2. And so you could certainly type that into your calculator and get an answer. But just to show you where our method's going to come from, I could actually factor out a couple things. I could take that pi and just bring it out to the front. And then I'm going to almost take that 2 that they have in common and factor that towards the back. And then what's left behind would be an 8 squared minus a 3 squared, which seems like a really odd way of solving it. It would be, but the point I want to make is that a formula for anything like this could be pi times the outside radius squared minus the inside radius squared, and then with your thickness, or a dx. And so that's going to be where our formula for this idea comes from. And so this just is stating that formula. It's very similar to the previous one, where we have a pi out here. We have our limits from a to b, and then on the inside we have an r squared minus an r squared. Just the capital R means the big outside radius, and the lowercase r means the small inside radius, and then a little thickness. And so I think one thing to note is that we need to, for a washer method, square both of the radii. So what we're going to do for this video, we're going to look at 4 examples, but they're all going to deal with the same shape. Excuse me. And we're going to be revolving this shape around different axes of revolutions. But they're controlled by 2x squared, by y equals 0, and by x equals 2. So it's kind of the area that's in here. And I know my 2x squared looks pretty bad, but good enough. And then I just want you to note that there are going to be times where we want to take this equation and solve for x. So if you did the algebra, we could also say that x equals the square root of y over 2. So for the first one, what we're going to do is revolve it just around the y-axis. So kind of around here is how we're going to revolve it. And so the rectangle then has to be perpendicular to the axis of revolution. So my rectangle that I would be thinking of is kind of like this. And I need to measure from the axis of revolution. So I need to think about starting from here. I have to think about what that outside, well, first thing is, if I'm going to revolve around here, I need to notice there's a gap. And so that is a clear sign that this is going to be a washer method. Whenever I see that gap starting from the axis of revolution going out, be thinking about that. And so I'm going to have an outside radius, which I know is always 2. And then my inside radius is whatever this x value is here, and that's related to the curved function right there. So that's going to be this x value right here. So if I had to set up my integral for this, I could just say that the volume is going to equal, the formula says, a pi, and then the integral sign. I need to think about my limits. So because I'm going, my rectangles are kind of going up and down this way, I have dy's. I need to find the y values for these intersections, I'm going to be putting rectangles in all the way from 0 all the way up to 8. So from 0 to 8. And then I need to write out the outside radius. We said measure from here to here. That's a radius of 2, so I'd have a 2 squared. And then I'm going to subtract the inside radius. The inside radius was this x value right here, which is just going to be the equation square root of y over 2. And that also needs to be squared because that's a separate radius and then a dy. And so this is not necessarily asking us to solve the equation, just to write out an integral notation for it. So we could certainly stop there, but just to show you that we could simplify it a little bit, it could just be pi integral from 0 to 8 of 4 minus y over 2 dy. And that could be our answer for this particular question. The next part says now revolve this around the x-axis. So we're going to be revolving right there. And so the shape is directly connected to it, and that's going to be a sign that this is just a little bit of review. This is going to be the disk method. And so the setup might look a little different. For the disk method, to find the volume, we go pi with the integral symbol. Now my rectangles are going to be like this. So I guess I should have done that first, because now you can clearly see it's connected to the axis of revolution. My lone radius is just whatever that y value is from the x-axis all the way up to that curved function, and that is 2x squared. So I could write in 2x squared, and I would need to square that because that's the radius for this with the dx. And then the limits are going to be whatever the x values are for these intersection points. So in this case, it'd be from 0 to 2. So again, I could certainly simplify this a little bit. 2x squared is going to be 4x to the 4th, and then dx. So that's not so bad. The third example, now we're going to revolve around the line y equals 8. So if I were to just kind of draw that in here, we're going to revolve around this. And so now if I were to draw in a rectangle, I could even use the same rectangle I had on that previous example, but that rectangle is never going to touch the axis of revolution. So that is a sign that this will be a washer method. And so I need to, again, think about how do I come up with the equation for this. And this one is probably the most complicated, I say, for this entire lesson. It starts out kind of the same way. The volume is going to be pi times, and then we can integrate. Now again, the limits would still be from 0 to 2 because I'm going to be filling these rectangles in all the way from 0 to 2. But as I rotate this around, the outside radius is going to go all the way from here down. So that would be 8. And I have to square that. The inside radius is going to go all the way from here down. So I need to really think about how I could measure this idea. And so it's going to be hard to come up with a way just to get this by itself. What I need to do is think of going this entire distance minus this. Okay, so this entire distance is an 8. This entire distance is the y value, and that's going to leave me this right here. So I have to be really careful with that. That entire inside radius would be an 8 minus the y value, while y for that is just 2x squared, and that's going to get me what's left over. So think carefully about that. Certainly ask a question on that if you're a little stuck. And I'm going to put in some square brackets here just so we realize that all of that would have to be integrated. Now this can also be simplified a bit. So I'll take a minute just to write that out so you can see where all this is going. 8 squared is 64. And then all these pieces that are coming from foiling 8 minus 2x squared, I need to make sure that I subtract them. So if I were to foil 8 minus 2x squared, and go ahead and try this a little bit, I'd get a 64. I'll do it like that here. And then from the 2x squared times an 8 and another 2x squared times an 8, actually it would be a negative 2x squared times an 8 for both of those. That's going to get me a negative 32 x squared. And then the negative 2x squared times a negative 2x squared gets me a positive 4x to the fourth. And all of that would have to be subtracted. Okay, so it gets kind of messy here for just a second. Okay, but then once I get there, 64 minus 64, that goes away. The 32x squared becomes a positive, and then it'd be a minus 4x to the fourth. Let's put that in parentheses so we realize we integrate all that with the dx. So this would probably be the easiest thing to work with right there. And then our last example, now we're going to rotate around the line x equals 2. And so it would be around here. And so if we were to draw in a rectangle again, kind of like that, if we're going to rotate around this line, it is connected. That is a sign that it is a disk method. And so it's going back again to the previous lesson. So the volume for this, there we go, is going to equal a pi, and then we integrate all these rectangles that we're shoving in there. Because my rectangles are horizontal, I'm going to be looking for the y values as I slide these rectangles all the way through here. So that's going to be from 0 to 8. And again, disk method, I have one radius. I need to start measuring from here. So how do I measure this from here to there? And the easiest way to do that is to say, well, what's this entire distance minus this little piece right here? So this is 2. And remember, this is all one radius right now. Okay, I'm trying to represent one radius because it's the disk method. So it's going to be 2 minus that x value. That x value is related to the curvy part, so the square root of y over 2. Okay, when I do this, I am left with this distance. And that is what I want for my one radius that I'm using. So instead of squaring both parts like I've done in the washer methods, this is just representing one radius, so I square that entire thing and then have a dy at the end. So I think that is a big challenge for this lesson here. Is the first two I think maybe made a little bit more sense, A and B. C was really complicated, and now D, it's not as bad, but you got to be really careful by recognizing, are you having two radii and you have to square them individually, or even though you have a complicated idea here, it's really just representing one radius. And so you square the entire chunk as one big idea. So we could definitely simplify that a little bit more, but this might get a little bit messy, and I have a feeling this video is already getting a little bit too long, so we're just going to call that our answer for this one. So again, jot down some questions. I know it's a complicated idea, but try to write some very specific ideas down about what you want to talk about in class tomorrow.